Hi everyone, my name is Colin Hank. If you see me around, please call me Colin. I wanted to take this opportunity to quickly go over a little bit about the General Chemistry Lab course, and then I also wanted to go over the Experiment 1 details that we have for you. I'm going to do this in person starting in a few weeks, but because we have the first 2 Mondays off as holidays, I'm going to do the first 2 experiments via Blackboard, well, actually via YouTube, making a video like I'm doing right now. So first thing I want to do is go over some general information about the chemistry lab, and you probably heard this information in lab this week. However, I do want to go over it one more time just because it's really important. We throw a lot of rules at you, and the reason we throw a lot of rules at you is because we want to keep you safe. And we do have to ask that you follow these rules, unfortunately, so that's really important. So I want to go over some of those rules. But before I do that, I just want to give you a general idea of how the lab is going to go. So basically, you're going to come to lab next week if you have lab Tuesday through Friday. And if you have lab on Monday, obviously it's a day off. When you come to lab next week, you're going to do a recitation session. The recitation is going to be a couple of hard problems from the general chemistry lecture. At the beginning of the course, it's somewhat challenging for us to make hard problems, but there's going to be a couple of problems, and you're going to work in groups. You can use the internet, you can do whatever, use your book, use each other, but you can't ask the TA. And basically, you're going to work through these challenging problems. And this is to give you an opportunity to solve a hard problem. After that, you're going to turn it in. If you get it correct, you'll get 10 points. If you make an honest effort, which I know all of you will, you're going to get 8 points. If you were to get 8 points, said another way, make an honest effort on all of the recitations, you will get full credit. So you don't even have to get a single one right the entire semester. You just have to make an honest effort. However, solving hard problems is good. It makes you smarter. So, if you want to get the most out of this, make your best attempt to solve these problems. And hopefully, throughout the semester, you'll get some of them correct. Now, after recitation, you're going to do the actual lab. And the first part of the lab is exactly just like the homework. You're going to go over dimensional analysis, graphing, and accuracy and precision. And if I'm here on the Blackboard site, if you go to the announcements, you can find a link to a YouTube channel, which is 3 videos, that will help you get the homework that you got this week. If you didn't get the homework this week, or you lost it, or whatever, if you go to the beginning of semester's materials, you can click on homework due with experiment 1 and get another copy. So there's basically 3 types of things. There's dimensional analysis, graphing, and accuracy and precision. And you're going to do paperwork stuff on this in the lab. This homework will help you to do that. As I mentioned just a second ago, these YouTube videos will help you do the homework. So please watch them. They're about 20 minutes in total for all 3 of them. Basically, watch one, do the homework problem, watch one, do the homework problem, so on and so forth. Then after that, you're going to do the actual lab. And to do the actual lab part, this is actual lab, I mean, you're going to do it during the lab class, but to do the actual lab part of the lab, where you're going to mix chemicals together, there are lots of rules. To help you to remember these rules, I again suggest you go to beginning of semester materials and you click on this experiment 1 checklist. So beginning of semester materials, experiment 1 checklist. And this is a checklist of the things that you need to do. The first thing you need is a signed copy of the laboratory safety guidelines. So you can find this in the beginning of your lab manual. You can also find this in course materials and information. There's chemistry lab safety PDF. And if you open this up, it's about 13 pages of safety information. And at the end of all of this safety information is a consent form for you to sign. Every student must have a consent form when they show up to do experiment 1. So please make sure you read this, get it from your lab manual or print out a copy, and you bring your consent form, to experiment 1. Now I want to go back, not to my grades, I want to go back to the first week checklist. What else do you need? You need to have proper PPE, gloves, goggles, and a lab coat. These can all be purchased from Chemistry B44 in the basement of the chemistry building. Now, I want to warn you, if you go 5 minutes before your lab starts, there may be a long line. At any given time, 80 students take the lab. So if you're number 79 in line and you're there 10 minutes early, you're probably not going to get them in time. I strongly recommend you get these things this week, as that will help you. While you're there, you can also get a copy of the lab manual. This is also sold in Chemistry B44, so I'm dropping down to this one. You are going to need a copy of the lab manual. If you don't want to get a copy of the lab manual right away, you can go to this trial pack and you can actually download Experiment 1 if you want to take a look at that. But I recommend you get a lab manual because you're going to need it anyway. Now I'm going to go back to the Experiment 1 checklist. You need to be dressed appropriate for lab. That means completely covered legs and feet. No sandals, no shorts. You have to have completely covered legs and feet. Please make sure you're dressed appropriately. Today happens to be a heat wave in Albany. I think it's supposed to be the same tomorrow. It doesn't matter if you were to have lab today, none of you do, or you're actually going to do an experiment, you have to have completely covered legs and feet. All right, so throw a pair of sweatpants in your backpack or whatever the case may be, and a pair of sneakers, but make sure you have completely covered legs and feet. We can't allow you to do the lab if you don't have this, and we don't want to make you mad by making you go home and change, but we will because this is kind of like a legal thing, and you have to have completely covered legs and feet. So, the next thing is I have read the lab experiment and completed my first lab write-up. You should have done this during lab orientation this week. If you haven't already done it, talk to somebody who has and make sure you have this completed. I'm also going to go over a lot of this in this video. And I have completed the dimensional analysis, graphing, and accuracy and precision homework. We already talked about the homework that is due, and those are the first 3 parts of the experiment. They are paperwork, but make sure that you've completed that before you come to lab. I strongly recommend you actually print out a copy of this checklist and you make sure you've done all of these things before you walk over to come to your lab. We don't want to tell you you can't do the lab, but if you're wearing shorts, we just can't allow you to do it. Now we have a few extra lab coats and goggles available for you to borrow, but if 10 people show up without lab coats, we simply just don't have that many to loan out. So just be aware that you need to follow all of these rules. Again, these rules are meant to keep you safe. I know it's a pain in the butt. I know no one likes to follow rules and it's a pain, but it is what it is. We are here to help you learn chemistry, but there are some basic things that just have to be done. So please take care of these basic things and then you'll be good to go for lab. Now I'd like to move on to experiment 1. And what I would like to look at is some of the requirements for experiment 1, and specifically the dimensional analysis of the 3% NaCl solution, the part of the lab that you're actually going to do during lab. So this is what you need for your experiment 1 pre-lab. You've probably already done this. You did it in lab this week, but you need a title, an objective, a hypothesis, of variables, an experimental outline, chemical hazards and waste, and key math equations. So these are the parts of the pre-lab that are required for the first week, and for every week for that matter. Note that this is probably 90% of the lab write-up. So you write 90% of the lab write-up before you get to lab. You then write a conclusion, and then you're done. So that's basically how it works. Of course, you also have to do the experimental part. Now, before we talk about all of these sections of the first pre-lab, and then I will go on to things that you haven't seen before during class. I will actually show you how to manipulate your data once you get it, and a little bit about how to use Excel, so you want to stay tuned for that. But before we do that, let's talk about what we're actually doing in this experiment. And we have these nice pictures, so I figured we'd use them. This is right from the lab manual. I got it off a Blackboard. You may have a copy of it that you purchased, but this is from the lab manual. So the first thing we're going to do is we're going to take an Erlenmeyer flask, we're going to put it on the balance, and we're going to tare it. So we zero it out. So we zero out the Erlenmeyer flask. We then add between 0.74 and 0.76 grams of salt to the flask. So you can see, I think this was actually me, here, adding the salt to the flask. Notice I have my left hand over here to hold the chemicals, and my right hand, I'm right-handed, over here to hold the spatula. This helps minimize spilling. So I'm going to add 0.74 to 0.76 grams. You'll notice I added 0.751 to the tiered flask. Then after that, I'm going to add 24.2 milliliters of water as measured in a graduated cylinder as shown here. And I'm going to swirl that up. And that is my 3% NaCl solution. So now I've made my 3% NaCl solution. Now what I want to do is take the mass of three of these clean, dry, and labeled 50 milliliter Erlenmeyer flasks. So these are little Erlenmeyer flasks, and you're going to get three of them. They need to be clean, they need to be dry, they need to be labeled, and you're going to record the mass of all three of these flasks. You're then going to pour 1 milliliter of the 3% salt solution that you made previously into each of the flasks. So using a graduated cylinder, we add 1 ml to this flask, 1 ml to this flask, and 1 ml to this flask. We're then going to boil off the salt on a hot plate. So you'll see this hot plate here is heated to 400 degrees. This is dangerous and can burn you. All right, this is like using an oven at home, or a stovetop more accurately at home. So it's hot, be careful. And we're going to put these flasks onto the hot plate, and of course the water is going to boil off. Note that the salt does sometimes fly out of the flasks, so don't stick your face right above the flasks because it can fly onto you, and that's a little bit dangerous, and of course it's hot. So basically, we're going to put these three flasks on here. The water is going to boil off, and the salt is not. And we'll talk later on, you'll talk later on in the lecture course about why the salt doesn't boil. However, the water does. So the water goes away, and what you're ending up with is three flasks with some residual salt in them. And what we want to do is test the accuracy and the precision with which these flasks contain a certain amount of salt. Now in the videos for the accuracy and precision part of the pre-lab, I talk in great detail about what accuracy and precision means, and I don't want to repeat that here. But I do want to note that we're going to measure accuracy by percent error or percent difference, and we're going to measure precision by relative standard deviation. So that's basically that. Once we have the flasks with the water boil off, we weigh them again, we record the mass, and we figure out how much salt is left in the flask. That's the experiment, the whole thing. So now that we have an idea of what's going on in the experiment, we can go back and talk about our pre-lab. All right. And when you're doing your actual pre-labs, I strongly recommend that you do it this way. Read the experiment so you have some clue of what's going on in the experiment before you try to write all of these sections of the experiment. It'll make your life much easier than if you're trying to figure out these details as you read it. Read it through once, then go back, and of course you can look again. So we need a title for this experiment, and our title is Dimensional Analysis of a 3% NaCl solution. So that is a good title. We need an objective. Our objective is a little long. Yours may not be that long. This is like writing any other paper. There's no one right answer, right? There's no one right paper about U.S. history. There's an infinite number of good papers about U.S. history. So it's the same thing in a lab experiment. There's an infinite number of good lab experiments. This is just our example. It may have a little more details than you would have. So our objective, when an objective generally speaking is a short statement of the goals of performing the experiment, our objective is, the objective of this part of the experiment is to experimentally determine the amount of salt in 1 milliliter of a 3% NaCl solution over 3 trials. After the mass of the salt in solution of each trial has been determined, the accuracy and precision of the experimental results will be discussed. And of course, to discuss them, we need to calculate them. The next part is the hypothesis. Hypothesis means many things, but in this course, it means two things. It means first the usual thing, a prediction of what we expect to happen. So a hypothesis usually includes a prediction of what we expect to happen and why some scientific explanation or why we expect it to happen. So in order to predict what we expect to happen, we need to do dimensional analysis. And I go over in the other video for the earlier part of the homework and for the lab experiment, dimensional analysis. So I don't want to go over it in great detail here. But I do want to do the specific dimensional analysis that you're going to need for this part of the experiment. in order to predict how much salt is going to be in the flask, we need to calculate how much salt should be in the flask. So this is a 3%, actually it's a, move this down, 3.0% m over v, mass over volume, NaCl solution. And what this means is that 3 grams of NaCl equals 100 milliliters of solution. Percent means part out of 100. Well, if it's 3%, that means 3 parts, 3 grams of NaCl, equals 100 wholes, or 100 milliliters of solution. So you can convert any percentage into an equality this way. If you get 80% on an exam, 80%, that means 80 correct per 100 questions. Well, probably more accurately, points. Right? It means you get 80 points for every 100 points there are. Well, here it's 3%, so you get 3 grams for every 100 milliliters there are. Percentage is part out of 100. Well, this equality is very important because now we know we're starting with 1.0 milliliters of the solution. Times, we now want to use dimensional analysis, which is a fraction. We want milliliters of solution to cancel. So in all dimensional analysis, you're going to have one thing equal to another thing. And you're going to want to put one of those two things on the bottom and one on the top. The thing on the bottom is the unit you want to get rid of. In this case, 100 milliliters of solution, because we want milliliters of solution unit to cancel out. And on top, 3.0 grams of NaCl. And when you do this math, you find that there are 0.030 grams of NaCl in 1 milliliter of this 3% solution. Note that this is very little. This is 30 milligrams. And this is going to cause a huge experimental error. Now, we did that on purpose. We gave you an experiment to begin with where there's lots of error because we're talking about error. That's what we're trying to learn about here, accuracy and precision. So we gave you one where you're going to get a lot of error. Don't be surprised if you don't get quite 30 milligrams. A drop of water weighs approximately 30 milligrams. So give or take. So this is basically the dimensional analysis. Now that we know what to expect, we can write our hypothesis. So the first sentence is, each 1 milliliter sample of the 25 milliliter 3% NaCl solution should contain 0.030 grams of NaCl, because 3% saltwater solution is a homogeneous mixture with uniform composition throughout. So we have a clear prediction of what we expect to happen. Each mill sample should contain 0.03 grams. And we have a scientific explanation of why. Because it's a homogeneous or homogeneous mixture with uniform composition throughout. This is very important, and you'll learn more about this later. We added one more sentence, maybe not completely necessary, but just makes it sound a little bit better. Therefore, after boiling off the water from each flask, the same 0.03 grams of salt should remain, as the salt's boiling point is too high to evaporate. So salt does not evaporate because it has a high boiling point. I'm not sure that's entirely necessary. I think you'd be okay with the first sentence, but it is some good additional information. Moving along, we now need to identify the independent and dependent variable. So the independent variable is the variable changed by the experimenter. That's the one that we actively change. And the dependent variable is the variable that we observe and record. So in this experiment, saltwater concentration and volume are the independent variables. Pick one. All right, there's usually lots of independent variables. You could even argue the temperature of the hot plate is an independent variable because the experimenter controls that. What we don't control, or what we're trying to figure out, or the dependent variable, and there's usually only one, and in good scientific experiments, we're trying to minimize the dependent variables, The mass of the salt in the 1 milliliter aliquot is the dependent variable. That's what we're trying to figure out. We're going to boil off the water and we're going to measure the mass of the salt that remains. That is the dependent variable. Experimental outline, we already covered this at the beginning. And when you're actually doing your work, it can often be easier to write the experimental outline first, because the experimental outline, as we mentioned before, is what gives you an idea of what's going on in the experiment. So here is the experimental outline. Chemical hazards and waste. In this case, the main hazard is that the hot plate is very hot. Also, the salt does tend to fly out of the flask sometimes, so you need to use that. Use caution. Don't stick your face right over it. You don't want to stick your face right over a hot plate, just like you wouldn't stick your face over a hot stove or a hot stove top. Then finally, the key math equations, and we already covered this. Okay. We needed this to actually write the hypothesis and make our prediction, but this is the dimensional analysis that we covered earlier. So now we have a good pre-lab. Now, of course, if you haven't written the pre-lab, you can just pause this video and copy ours, but try to think your way through it. And the better you do at getting it, or the better you are, more familiar you are, I guess I should say, with writing these pre-labs, the more it'll help you later on. All right, you won't be learning the format, you'll be actually doing the work. Also, I should mention for later pre-labs, we do have some guidelines to help you write the hypothesis. And they literally say stuff like sentence 1 should contain, and then it tells you what sentence 1 should contain, sentence 2 should contain, and so on and so forth. And I'll show you that for the conclusion here as well. All right, so now we've written our pre-lab. We know what's going on in the experiment. We're going to make this 3% saltwater solution as we talked about. We're going to make 3 samples with 1 milliliter aliquots. We are then going to boil off the water and we are going to measure the mass. What's really important is that we take down all this data. And I strongly recommend that you learn how to use Excel. All right, probably many of you already know how to do this, but if you don't, spend some time to learn how to do this. Even if you do nothing that has anything to do with chemistry, and let's say you become a teacher of English, you can use Excel to calculate your students' final grades, and it will make your life easier. Okay, there are lots of you in this course, as you know, and we use Excel to calculate your final grades. Knowing how to do that has nothing to do with chemistry, it's just a useful skill. So I strongly recommend that you learn how to do this. It'll also make your life easier, and everyone likes to make their life easier. All right, so what do we have here? Okay, and you could pause this video and you could copy this right down into your own Excel file if you wanted to. We have flask number. We're going to use 3 flasks. Okay, these are the 50 milliliter Erlenmeyer flasks, the little ones. We have the mass of the empty flask in grams. I made these up. Yours may not be exactly this. I used the lab manual as a rough guide of how much they'd weigh and or what their mass would be, and then I made these numbers up. So don't be alarmed if yours are not exactly like this. Believe it or not, they can have significantly different masses because different manufacturers use different thicknesses of glass, and the thicker the glass is, of course, the heavier the flask is. Mass of flask and residual salt. So this is after we put in the 1 milliliter of water and we boil off the water, how much, what is the mass of the flask and the salt that's left? And then of course the mass of the salt, which is what we need to calculate. So these are basically all we need to write our lab experiment and take down our data. You can, of course, have this ready to go before you walk in the door. And for this one, I'm actually going to show you all the formulas at the end of the video so that way you can figure this out. So let's take a look. All right. So I'm going to also make up these numbers. All right. And these are the masses of the flask after we've boiled off the water. So this one is 38.4071. This one is 39.3890, and this one is 37.3218. All right, notice that the balance has 4 decimal places. Most of them do, some of them only have 3, but if they either have 3 or 4 decimal places, I'm writing them all down. These numbers matter, okay? We pay extra money for balances that have these many decimal places. So please use them. All right, if you're trying to measure 30 milligrams, it's very important to use a balance that has at least 4 decimal places. So these are experimental data. All right, this is the flask before you started. Clean, dry, labeled flask. Put it on the balance and weigh it. I'm just going to label them 1, 2, and 3. Then I'm going to boil off the water, and this is the mass after. Now I want to figure out the mass of the salt. Well, how am I going to do that? First of all, to tell Excel to do math, we type equals. Then I want to take the mass of the flask and the residual salt and subtract, just hit the minus key, the mass of the empty flask right here. This will give me the mass of the salt. I'm simply hitting enter and Excel does the math for me. Now here I could do the same thing, equals this one minus this one and hit enter and it does the same thing. Or I can just grab this one and pull it down. Okay, notice that that Excel is just like a calculator. It doesn't necessarily give you the right number of significant figures. I can use this to add more or less digits, but we're not real picky about your sig figs in Excel. We just want you to be aware that it's just like a calculator. It doesn't necessarily give you the right number of significant figures. Now, what did I say I wanted to calculate? Well, I have the mass of the salt in my 3 trials. And in order to finish this lab experiment, I need to do accuracy and precision. Precision, or reproducibility, is measured by relative standard deviation. So we need to calculate the relative standard deviation. In order to do that, you can either do it all at once or calculate the average separately. I'm going to calculate the average separately. So in order to average these numbers, I type equals average. Excel knows how to average numbers. Then I highlight the numbers that I want to calculate the average of and press enter. Excel gives me the average. Now I want to calculate the relative standard deviation. Relative standard deviation in parts per thousand. And I should have mentioned the average is in grams. The relative standard deviation in parts per thousand is equal to the standard deviation divided by the average times 1,000. So to calculate standard deviation, Excel knows how to do that. STDEV, open parentheses. Select the data, close the parentheses. Divide by the average, this is the average, times 1,000. That is my RSD. Remember that an RSD of 0 is ideal, right? If there's no deviation in the data, the RSD will be 0 and the precision is excellent. 230 out of 1,000 or 23% is probably better than many of you would get actually experimentally, including myself. I made these numbers up, but it's not the best precision. Okay, now we want to calculate the percent difference or the percent error, and that's going to be a percentage as the unit. And in order to do that, we want to take the absolute value of the actual value, the accepted value, 0.03 grams, minus the experimental value, the average, divided by the accepted value times 100. So to do absolute value, type equals ABS for absolute value, this, 0.030 minus the average, divided by the accepted value, 0.030 times 100, because it's a percentage. And we get 325% error. Okay, so these, which again have a ridiculous number of significant figures, don't write this number of digits in your lab report, but on Excel it's fine. This gives us the average, the relative standard deviation, and the percentage error. Now I want to go back to the lab manual for 1 minute. At the very end of this lab experiment, it gives us a conclusion statement. So after you calculate this stuff in the lab, you're going to be asked to write a conclusion. And it says sentence 1 should contain one of the following: whether the results did or did not support the hypothesis. And the approximate amount of salt found in each of the flasks, and it says a single number should be reported. So let's look at what should go in sentence 1. The results didn't closely fit the hypothesis. Remember, we hypothesized we'd get 0.03 grams. So the results did not significantly fit the hypothesis because on average we saw 0.128 grams of salt in the 3 flasks. So we did not fit the hypothesis because we're nowhere near 0.03 grams. And this is relative. You could ask, what is near 0.03 grams? And it's relative. Depends. All right, but use your judgment. Sentence 2 should state the RSD of the mass percent calculated for the 3 samples. So the RSD here is 230. So the relative standard deviation of the mass percent is 230. That's the sentence. That's pretty straightforward. Then finally, sentence 3 should contain the following. This indicates that the solution was not a homogeneous mixture or was a heterogeneous mixture because the RSD is very high, right? So the samples have very different masses, and therefore the precision was very low. And that is basically that. So we're essentially using the fact that there's a large percentage error or the fact that it's not very close to 0.03 grams to say that our results did not support the hypothesis. We're further saying, based on the RSD, that it's not even close, and it's also not precise. So it's not reproducible, which supports that it's a heterogeneous mixture. Of course, what actually happened is experimental error. Trying to weigh out 30 milligrams is foolish. It's way too small of an amount to measure out. So you're asking yourself, why did we have you do this? Well, this is about accuracy and precision. We don't want to give you something that's perfectly accurate and precise on the first try. So we give you something where it's very difficult to have good accuracy and precision. If you wanted to redo this experiment and make it better, there's a very simple way to do that. Don't use a milliliter of solution. Instead of boiling off a milliliter of solution, boil off a liter of solution, 1,000 milliliters. Now, if you're off by 50 milligrams, it's not going to make a big difference. Here, 50 milligrams is more than the salt you expect, so it's going to make a huge difference. However, if you boil off a liter and you're off by 50 milligrams, your accuracy and precision are going to be spot on. And solutions are homogeneous mixtures, so that would go ahead and reinforce the hypothesis. Final thing that I want to do before I show you the Excel calculations on the actual values here, the formulas. The last thing that I wanted to do is let you know that one of the most common errors here is people forget to record the mass of the empty flask. Or they measure it incorrectly and they get a mass of salt that's negative. Now sometimes this is unavoidable. However, if you either forget to mass the empty flask or you get a mass of salt that's negative, what you want to do is write down the mass after the salt is present. Make sure you record it. Then clean and dry the flask. Rinse it out with water and wipe it dry with a paper towel. And then record the mass of the empty flask. If there's still an error, sometimes that happens because the flask was wet to begin with and you boiled off that extra water and therefore you still get a negative mass. But sometimes it fixes the problem. And it certainly fixes the problem if you forgot to record the mass of the empty flask to begin with. So that's basically just a common error that happens that we wanted to try and help you fix. So I hope you found this video helpful. I'd again like to welcome you to General Chemistry. I thank you for sitting through it. I know it's not the most exciting thing to watch on YouTube, but we do appreciate it, and I look forward to working with you this semester. Have a great day, and we'll see you soon. Now, as promised, I'm going to show you the formulas here so you could actually copy this down if you wanted to, and it gives you all of the formulas with the worked out solutions for exactly what you would actually need to type into Excel to get it to do exactly what my Excel file does.